thank you very much for inviting me. It's always lovely to talk to students because unlike when you're talking to faculty, you guys listen. So it's a polite audience and you're not sitting on your laptops. So it's wonderful. I'm going to be talking about something a little different, although not completely unconnected to the previous talk, because actually I thought you were referring to heavy ion collisions when you were saying testable. And we could have that discussion at the coffee break if you want. So what we do is basically melting nuclei, and I'm going to explain a little bit more about what I mean by that. So as you guys know, normal matter is made up of protons, neutrons, and electrons, and then the protons and neutrons are themselves made up of quarks and gluons. And you guys have probably seen a picture similar to this. I like the one with animals, and I had to add my own Higgs by hand, so I went with a brontosaurus because by mass scale, that's roughly right. But most of what I'm going to be talking to you guys about is quarks and gluons, because what we do is that we melt these nuclei and form what we now know is a liquid of quarks and gluons. And I'm going to be talking about what we directly measure is hadrons, and there's different types, and they're all made up of quarks and gluons. There's a whole bunch of names. You don't need to remember the names, just that there's a lot of them, and you can think of them as analogous to chemicals. Just like you can come up with different chemical compounds by different combinations of atoms, you can come up with different hadrons by different combinations of quarks and antiquarks. So this is the phase diagram of nuclear matter, and what I like about this phase diagram is that this is actually pretty close to quantitative for what we knew when I started graduate school. We've gotten a little bit better, but there's not much information on there. So the scale here is temperature in GeV, which is very hot. This is around 1 million times the core of the sun. This temperature is this axis is baryochemical potential, which is roughly the amount of energy that you need to create a new baryon. Now, here, when you're here, what happens is that you have free energy in the system, so you're actually creating a baryon and an antibaryon. So you can create baryons, but your net number of baryons is not that high, is not increased. And up here we have what's called the quark-gluon plasma, which we know is a liquid of quarks and gluons, about 1 million times hotter than the core of the sun. Normal nuclear matter is down here, basically on the axis on this scale. And then these, as you go to higher potentials, it's been hypothesized that there's stuff out here in neutron stars, but we can't directly access that experimentally. So how do we get to these temperatures that are about 1 million times the core of the sun in the laboratory? Well, what we'd like to do, you just heat it up and then you have this little vat of QGP and you can study it. We can't really do that in practice. So what we do is that we compress nuclei until the nucleon boundary is irrelevant. And how we do that in the laboratory is that we take nuclei, we strip them, we take atoms, we strip them of all their electrons, and then we accelerate the nuclei to very high speeds, smash them together, they very briefly melt, and then the system expands and cools, refreezing, so forming new hadrons, and what we directly observe in our detector is these hadrons. This is somewhat analogous to if you took 2 ice cubes in outer space, got them going really fast, sped them up, smashed them together, you would very briefly melt them, and the system would expand and cool, and you could determine the properties of water from looking at those ice shards as the system expands and cools. It's hard, but it would work. So what we actually have to do is figure out how we infer the properties of matter from this melted nuclear matter from these frozen shards of nuclear matter. And I'm going to tell you a few different ways that we can do that. Here are, you have in every high energy talk, you have pictures like this. These are the colliders we can do this at. This is the relativistic heavy ion collider on Long Island in New York. This is the Large Hadron Collider. For scale, this is, if you drew the relativistic heavy ion collider on top of the LHC, this is how large it would be. The LHC is actually underground, so you can't see it if you fly over. Unlike Rick, if you fly into JFK and get put in one of those annoying holding patterns, sometimes you'll fly over Long Island and can see Rick, or if you ever fly into Islip Airport. So I've done both. Whereas, for context, here's the Geneva Airport. So here I've shown the different detectors that we have. Actually, I see that some of them disappeared on my slide, and I need to edit my slide again. But what we can do here is that we actually are able to move around on the phase diagram. So a lot of the things that you hear about for particle physics, they really just want to go to higher and higher energies because they want to create more and more massive particles. We're interested in moving around the entire phase diagram so that we can map it out. So Rick is much more versatile. So it can cover about an order of magnitude in collision energy. And if you look, this shows roughly the trajectories where we can move along on the phase diagram at Rick. And the LHC has the highest energy collisions, so we can get the hottest and most longest lived quark-gluon plasma, which is what we call this liquid. So here are bigger pictures of the detectors that actually that we actually use for scale, and I'm going to focus on this one, which is the one that I do most of my work on. So here you can see the ELISE detector. No high energy talk is complete without a picture of a detector, and they kind of look the same if they're not your detector. So here you can see for scale, this is the size of a person. It is huge. This is actually this is a large red magnet, and this is one of those cases where it's convenient to be a small person, because when you go in to work while the magnet doors are closed, you have to climb through a hole that is this large, and that is fairly easy for me and not so easy for all of my collaborators. So I have become much more appreciated for being small. You also have to scale the side of the detector to work on things and fix it, which is fun, but a very different skill than what you study in your classes in grad school. And the whole purpose of all of this is that you're basically taking a picture of each of the collisions. So these collisions happen about 1,000 times per second. And what you probably learn about in your classes is bubble chambers, and those happen slowly enough that you could actually see the particles move through the detector, but you can't do that when you have 1,000 collisions per second. So we have a bunch of different sub-detectors, and each of these have different purposes. And one are trigger detectors. Those are basically, those tell us when to take a picture, when the collision actually happened. And then tracking detectors, these are mostly sensitive to charged particles, and they tell us where the particles went. So far you can think of this as having basically a black and white camera, a black and white picture, that you know that there was something there and you know where it was, but you can't tell what it was. You can't tell colors very well. Then we have particle identification detectors that can tell us what type of particle it was, and calorimeters that tell us how much energy it had. And these I think of both of these as like giving the photograph color. And the analogy does break down at some point, but it goes pretty far. So the final product that is actually what my students start with when they analyze data is something where they see the tracks. They're not actually dealing with the raw data. So here you can see an event display from a proton-proton collision. It's only in 2 dimensions. You're looking down the beam pipe here, and then it's in a magnetic field, so you see the charge tracks curving. These are calorimeter hits, and the colors correspond to how much energy the particle has lost, and heavier particles lose more energy in the detector than light particles. And this is all well and good. These collisions have on the order of about 50 tracks on average, which is not too hard, where it's not too hard to figure out which hits along the trajectory belong to which particle. This is a central lead-lead collision where we have about 2,000 tracks per collision, and then the issue of tracking becomes very complicated, and because we have to be able to tease out all of the signals from all of these different particles. So that is in itself a very interesting computing problem, not the one that I work on. But I'm going to show you then a video of what this looks like. I have learned through the years that you want to never be very careful about embedding effects into your talks because they often fail. So, and always test. So, okay, so this is outside of the PowerPoint. So here you are moving along with the particle along the beam pipe, and there's another particle coming from the other direction, and they're about to collide. They collide, and then the system expands and cools, and here you can see all of the particles fly out and hit the detector and leave tracks in the detector as they do so. CERN is very good at PR, so they give me lots of stuff to work with. And we'll do it again because I think it takes a couple times to really absorb it. So traveling along with the particle, they're about to collide. They collide, and the system expands and cools, and they leave tracks. And there are millions of channels of data read out. My experiment reads out terabytes per second. This poses all sorts of challenges that are very interesting. And it's actually one of the most amazing things when you have when you have millions of channels of detectors and several different sub-detectors, 1,000 collisions a second, and you have a lot of this actually built and tested by grad students, and you often are put in roles where you don't really know what you're doing. The most amazing thing is that any of this works at all. I mean, there's so many things that can go wrong, so it never ceases to be amazing to me that this actually works. So a few things of how I'm going to go through now. When we have that data, how do we figure out what we're actually studying? So I'm going to go through a few different approaches. So one is QGP chemistry. So I told you that we have all these different types of particles that we make comprised of quarks and gluons. So what you can do is that you can just take a whole bunch of different particles, count how many you have, and look at the ratios of particles compared to a model. And this is just like in chemistry when you get different numbers of molecules at different temperatures at equilibrium. We can actually use the ratios of particles to figure out what the temperature is. So here you can see the red are the data points and the blue are a fit of a model to the data. And what you get out of this fit is a chemical equilibrium temperature. And we even see, I won't go into the details, but we see that even strange quarks, which are a little heavier, reach equilibrium. And you can do this for several different collision energies. And we go from this phase diagram that we had earlier to what we actually have now, where we can use this to actually map out where this quark-gluon plasma freezes, and we get something that we call a hadron gas. So we're actually quantitatively mapping out the phase diagram. Now, that tells us what temperature the system was when the system froze out. It doesn't tell us what the highest temperatures we reached were, and we're also interested in that. Yes, and we think there's a critical point here. So there's a whole program looking for that critical point, which doesn't have we have a partial answer. We think that it's somewhere in this range, but we're not quite sure where quantitatively. So what we really want is we want to know what the hottest temperatures we reached were. And so how can we do that? I'm going to tell you about a few other ways that we can measure the temperature. And the first one is really cool. Well, they're all really cool. you guys have all heard of black body radiation, and I stole this picture off Wikipedia. And if you look at the distribution of photons emitted from some source, you can use that to measure the temperature of the system. So what we do here is the black line, the dashed line shows the expectation for the production of photons from quantum chromodynamics in the absence of a plasma. So this is for the purpose of this measurement. This is the background. And these points here show what we actually measure for photons that are directly created in the collision. And you see that there's an excess above the QCD background, and you can, now the whole system is expanding and cooling, so if you just look at the distribution of photons, you can't immediately say that that gives you the temperature. You have to compare it to some model. So the raw inverse slope parameter, it corresponds to, we call it an inverse slope parameter because it's not quite a temperature, but something around 200 MeV. But you compare this to models that can actually, that have a lot of the behavior of the system and you get that you have a temperature between 400 and 600 MeV at the hottest point in the collision. So, and this has of course been done both at the relativistic heavy ion collider and at the Large Hadron Collider. So the details are much more complicated, but the basic principle is what you learn in introductory physics, which is a common theme, I think, in all subjects that you learn. One of the other speakers mentioned it earlier too, that the core concepts in introductory physics are really important and stick with you through your career. So the other approach is to look at what melts. So we have states of quarkonia. In this case, we call them bottomonia. This plot shows, this has both bottomonia and charmonia, which is a bound state between a bottom quark and an anti-bottom quark, and between a charm quark and an anti-charm quark. And by looking at, so this is the ratio of what was produced, so we can actually calculate the number produced theoretically, to what we actually observe. And what you see is that as you get to looser and looser bound systems, that you're less likely to find them in the final state. So this is somewhat comparable to if you have, say, if you have a vat of some unknown metal and you don't know how hot it is, you can drop stuff in it and see if it melts. So you throw an ice cube in, it's going to melt, but you throw a hunk of granite in, and it probably won't. And so you can get some constraints on the temperature by doing that, by just looking at what can actually survive in the system. And this is a better plot to show that. Here you see the binding energy, and then here you see the ratio of the number we still have to the number we expect. So 1 means nothing is melted. And we get, again, some temperature. There's a bunch of, if you have stuff produced on the surface, it doesn't actually melt because it didn't interact, so you never get quite to 0. But we, again, get a similar number that we think that the system gets to something like 400 to 600 MeV at the highest energies. So that tells us a little bit more precisely that we start here, and the system, as it expands and cools, goes down like, it follows a trajectory something like this until it refreezes and then goes into the pion gas phase. So another one I want to talk about, because this is one of the things I did, you can measure the energy density, which is a little bit different from the temperature. So back of the envelope calculations, if the amount of energy you have in these collisions is actually not that much. If you have a mosquito flying through the air at 1 meter per second and it collides with another mosquito at 1 meter per second, that's about the amount of energy that you have in these collisions, except that this is concentrated in a very small volume of a few Fermi cubed. So that's why you get these very high temperatures, is because you have very high energy densities. So you can approximate that. We don't have a precise way of calculating it, but what you do is that you calculate the rough volume of the system at its highest temperature by basically saying, okay, well, it forms some rough tube that's the area of the overlap between the nuclei, and then it took some time for the nuclei to form the quark-gluon plasma, so everything's traveling at roughly the speed of light. So in this dimension, it's the time it took to form it over the speed of times the speed of light, and your energy density is basically the amount of energy you measure divided by the total volume. And here you can see the measurements that we have of the energy density. There's details I'm fudging over. Ask me about them if you're really interested. We expect that a quark-gluon plasma forms at about 1 GeV per Fermi cubed. And what we get up to at the relativistic heavy ion collider is about 6. And at the Large Hadron Collider, it's a little over 12. So we get to something like 12 times the energy density that you need to form this matter. And we can measure it. That's I think, the one thing, if you don't want to remember, I don't care if you remember what it is, but that actually by using clever tricks and working, thinking of clever ways of doing it, you can actually measure things that are really hard to measure. And the final thing I want to talk about is analogous to UV visual spectroscopy. So what you ideally would do if you want to measure something that you have no idea what its properties are, you would want to send a probe through the unknown medium, and so you know the properties of the probe before it goes through, and then you measure how interactions with the medium change it. And a problem with this, we can't just shine light into something that lives about 10 to the negative 23 seconds, so we have to figure out a clever way of doing it. And what we do is that we use probes which were actually created in the collision. And this is what I work on. We use something called jets, which form when you have a quark or gluon in one nucleus scatter off of a quark or gluon in another nucleus. And because we expect this matter to be roughly opaque to quarks and gluons, we expect that quarks or gluons will travel through unscathed. In contrast, we have a built-in control as well that we expect this whole matter, the quark-gluon plasma interacts through the strong force, but we don't expect it to interact very well. I don't want to use strongly. We don't expect it to have significant interactions through the electromagnetic force. So electromagnetic probes we expect to just fly through unscathed. So that's a control, which is another nice thing. We're trying to measure something that's really hard. We have a control so that we can make sure that we know what we're doing. The complication is that, as you may know, we don't see quarks or gluons directly. We see their products, and as they fly out, they form these collimated sprays of particles that are called jets. And you don't have to worry about what they are, just remember they're messy and hard and really cool. So I professionally study messes. And here, so we expect, the picture that we expect is that we expect that when you have, the other nice thing about these jets is that they mostly form in pairs. So again, you have this built-in control because if you see one, you should have another which is, by momentum conservation, 180 degrees away. So this plot was from the ATLAS collaboration, and this is along the beam pipe, and it's in a weird variable, but just this is along the beam pipe, and then what you see is one jet here, and you see its partner 180 degrees away. And this is in a collision, which we say is peripheral. It was just glancing. The two nuclei didn't interact very much. And what we see in a central collision is that actually you have that other particle absorbed significantly, so one of the jets disappears. Now this is a lovely cartoon picture, but we want to look at ways of quantifying things. So I'm going to introduce this observable called RAA. And again, this is, I actually snuck it in and used it earlier. It's the ratio of what you got to what you expect. So if you have and you can also do this by measuring something like proton-proton collisions, where we don't think we form this quark-gluon plasma, and comparing that to nucleus-nucleus collisions. So anything above 1 is enhancement. You see more than what you expected. Anything below is suppression. And this is again, analogous to UV visual spectroscopy. That in UV visual spectroscopy, you look at how many of something. In this case, this is I believe, yes, this is an absorption spectrum, and you can compare what you see to the pattern of different molecules to figure out what you had here. Again, we get a different type of spectrum, but we're looking at how much was absorbed, and we can figure out the properties of the medium from that. And here you see a whole lot of particles, and the colors are each a different particle. The orange ones are our electromagnetic probes, and we see they are consistent with 1, so that's our control. And everything else is a colored probe, all sorts of different types of hadrons. And we see suppression of up to a factor of 5 at the relativistic heavy ion collider, and a factor of up to a factor of 10 at the Large Hadron Collider. So we see that this matter is actually opaque to colored probes. And we can actually do some pretty detailed theoretical calculations that I will not get into to quantify what the properties of this matter are from these measurements. And I will skip over that last slide. So take-home messages, if you remember nothing else, when we form these very high energy when we do these very high energy nuclear collisions, we very briefly form a phase of matter called a quark-gluon plasma. And this medium is incredibly hot and dense, and it is opaque to colored probes and translucent to electromagnetic probes. So we have lots of, maybe the really brief message is, we have lots of cool ways of measuring it, and you just have to take what nature gives you and find the right way to use it. So a little bit about me. Here are the various degrees and positions. I do a lot of work on women in physics. I am working on being a more effective ally for people of color, which is a very hard, big, and complicated problem. I am a parent, so here you can see my son. He's 2.5, and I put this one in because this is actually his first gay pride parade. We were walking home from the farmer's market, and I have to say, and there was the gay pride parade, and it's good that these are much cleaner than they were a few decades ago, so everybody was mostly clothed, and he just remembers the octopus. He wants to know when the man in the octopus suit, for whatever reason, there was a man in an octopus suit, he wants to know when he's coming back. So that is hard, having kids and a career. I also have many hobbies, and I will tell you more about my bees than you want to know. And things you can ask me about dealing with harassment, which is very hard, careers outside of physics, which I have inexplicably become an expert on because lots of people talk to me about it, choosing a mentor, and then managing this balance between having kids and a career. Thank you.
Thank you, Christine.